Thanks a lot for having me and for organizing such a nice event. So I will be talking about, about the problem whether what is the difference between generalized measurements and projective measurements in quantum theory, and this is work based on this recent preprint that I worked on this project together with my master's student Filip Maciejewski from Warsaw and colleague from Gliwice, Zbyszek Buchała. Sorry, I'm quite nervous as always. So the point is, let's start from the beginning. So quantum measurements. Maybe it's better if I don't use the mic. No, I have to. Fine. So. Why quantum measurements are useful in quantum theory? Because they uncover the classical information encoded in quantum states. So because of the Born rule, when you have some quantum state, when you measure it by some apparatus, you recover the output statistics by computing overlaps of effects of your measurement with a state. And then among all generalized measurements, projective measurements, they form a particular class. That is, their effects are orthogonal projectors on the relevant Hilbert space. And this class forms a strict subset of all measurements for any finite dimensional system. And then, generalized measurements have many applications in quantum theory, including an ambiguous state discrimination, minimal error discrimination, tomography, randomness generation, non-locality, as we heard, or steering, as we heard in the previous talk. However, there are tasks for which they are not, projective measurements suffices. So, for instance, when we want to discriminate pure states that are linearly independent, then projective measurements are optimal, or for single parameter metrology, that's also the case. And the question that I've been interested in recent years is what is in general the relative power between those two classes? So generalized measurements, POVMs, and projective measurements. And that part, hopefully I hope to give part of this the answer to this question in my talk. So, this talk will be about what generalized measurements you can simulate when you can perform only projective measurements on your system. So you don't need to use ancillas, but you can use also some classical resources that are available. So randomization, by which I mean that different projective measurements are, let's say, implemented with different probabilities. And then we can also do classical post-processing of the outcomes that we receive. And then this is actually a chunk of work. A class of measurements that are simulable in this sense was a subject of this paper that I did together with Leo and my collaborators when I was still in ICFO in Spain. But so we'll be talking a bit about this kind of measurements in my talk, but most of the talk will be about one more ingredient, that is when I allow for postselection. That is to say that, it will be interesting in measurements that we can simulate when we can do those three things, but on the top of this, we postselect upon non-observing some particular outcome. And that's the outline of the rest of the presentation. So first I will introduce some setting and general results. Then I will introduce some measure of non-projective character of measurements based on white noise that you add to the measurements. Then I will present result. Sorry, the question, I will address the question what measurements can be simulated when you allow for those classical resources in post-selection. I will apply those results to the problem of relative power of POVMs and projective measurements in the context of an ambiguous state discrimination. And lastly, I hope I will manage to get there. I present some results on implementation of the protocol that involves post-selection on IBM quantum device. So maybe, yeah, let's get started. Yeah, so we were working in fine-dimensional Hilbert spaces. So we have the object I will be interested in are n-outcome measurements in d-dimensional space. So there are tuples of positive semi-definite operators that sum up to identity, and the labels here, the outcomes of measurements. And then in this class, I can identify projective measurements that are measurements whose effects are proportional to projectors in this space. Importantly, the number of outcomes can be greater than the dimension because I can formally embed effects in different manner in the space of outcomes. Okay, so that's somehow for mathematical convenience. And now I can, using this notation, I can formalize notions of, like classical processing that we can do with measurements. So we can do randomization that corresponds to implementing measurements, different measurements with some probability. So when we have some measurement M, N, measurement M, then we can take their convex combination. In operational sense, is that the meaning of this is that with probability Q we implement one measurement, with probability 1 minus Q another one, and then the corresponding effect of a measurement is given by this formula, and it gives it gives us the structure of the convex set in the set of measurements, and importantly, extremal points in the set have at most d-squared outcomes. Right, and then another thing that we can do with measurements, we can classically post-process them, namely upon observing some outcomes, we apply some stochastic map to the output, which corresponds to applying some stochastic map on the level of effects of our measurements. Then the set of projective simulable measurements consists of measurements that we can implement using those three operations. So randomization, implementation of projective measurements on a relevant Hilbert space, and then classical post-processing. Fine. And let me just briefly mention general results. Yep.
Sorry, are you talking about implementing a map exactly?
I'm talking now about implementing a map exactly. Okay. Let's say. I mean, one can relax this question, of course. Right. So now, one general result that I wanted to mention is that, in general, this step of computing, of implementing post-processing is not needed, in a sense that if for a specific number of outcomes and specific dimension, if I'm interested in projective simulable measurements, then I can just take the convex hull, formal convex hull of all projective measurements. This is one relevant thing. Another thing is that for any dimension, dichotomic measurements turn out to be simulated by projective measurements, and therefore all measurements that can be simulated by two outcome measurements are themselves projective simulable. But in general, we don't really know what the set looks like. Still, for any dimension, you can come up with a measure that kind of indicates the non-projective character of a measurement. So we can take a dephasing channel, okay, that we implement to effects of our measurement. So they become noisy, and this T is so-called visibility of a POVM. Right. So when T equals 0, then our all effects are proportional to identity, and then it's very simple. That is to say, this measurement is simulable by projective measurements. And then, maybe on the operational side, because this map, the polarizing map is self-dual, because of this measuring, probably it was mentioned in the previous talk, like measuring this noisy measurement on a noiseless state corresponds to measuring the noiseless measurement on the noisy state. Yeah. And then in this work with Leo, then for a given measurement, one is interested maybe in the greatest parameter t, such that greatest visibility such that the measurement is simulable by projective measurements. And then in any dimension, you are maybe interested in the most robust POVM, that is to say the one that has the smallest possible visibility that, for which it can be simulated. And for qubits, the optimal measurement turns out to be tetrahedral measurement, and the critical visibility is 1/√2. And yeah, using pretty much similar ideas to the ones given in the previous talk, we were able to, let's say, boost the local model for generalized measurements of a Vernon state up to the visibility of this order. However, in general, we just have the lower bound on this critical visibility, that is like 1/d. In general, we don't know more. And now I can move to the result. How much time do I have? 10 minutes? 10, 5, 10. Fine, sorry. I'm still struggling after the chat. Yeah, anyway, so now, so now we add post-processing to the game. So we have randomization, projective measurements, post-processing, and post-selection upon non-observing particular outcomes. And then mathematically we define what does it mean to simulate a given measurement with post-selection with success probability t. So, okay, you can define it in operational way, but it turns out to be equivalent to the following formula. For a measurement m, there should be a scalar t such that such a noisy measurement like this equals to n, and n is projective simulable. So what it means is that this measurement n, when you post-select upon non-observing the last outcome, is exactly measurement m that you wanted to implement. So t has the interpretation of the success probability of implementing this measurement. Then one can ask, is it possible to simulate any measurement in this manner? And the answer is yes, as the title suggested. Right, and that's the subject of the first result I wanted to tell you. So for any dimension, for any number of outcomes, it turns out that you can simulate generalized measurement in this way for visibility equal to 1, for success probability equal to 1/d. Moreover, this number turns out to be optimal in a sense that you cannot get higher success probability for some measurements that you implement for some measurements on d-dimensional space. And then how the proof goes. First, there is like a constructive protocol that I will tell you later that attains this efficiency. Second, one can construct a specific measurements for which one can show that you cannot get higher success probability. And roughly speaking, the way, they are somehow, you construct them from the action of discrete Heisenberg-Weyl group. So they're similar to those measurements that are called SIG measurements. So anyway, you have a measurement that has d² number of outcomes, and then effects are proportional to rank 1 projectors that don't commute. And then the possibility for simulating such a measurement in this manner is very limited when you want to simulate it via projective measurement, and then you get some bounds that turn out to be exactly this number. Yeah. Now the protocol. So without loss of generality, we take measurements that have rank 1 effects. So therefore, every effect is proportional to some projector, and then those scalars that stand in front of the projector they sum up. They're positive, and they sum up to the dimension of the space. They can be used to yeah, they can be used to define a probability distribution. So the scheme, roughly speaking, works like this. So in the first stage, you choose some number I from 1 to n with probability equal to alpha I over d. Then upon this choice, you implement two outcome measurement, which is a projective measurement. You implement psi I or the negation of psi I. If the output was right, then you output I. Otherwise, you output this extra output n plus 1. One can prove that this measurement actually attains the success probability 1 over d. Yeah. Right, 5 more minutes, right? Something like this. Sorry. 5 minutes. Yeah, so now, yeah, application to an ambiguous state discrimination. So, yeah, this is the task when one is asked to discriminate states generated by some ensemble of quantum states in a manner that you cannot come up with false positive answers in the sense that measurement effects corresponding to the answer I should have overlap 0 with the state psi j. Yeah, and then because of this condition, it's like natural to consider P of EMs as good candidates for this task. And then one can wonder what, for a given ensemble of states, what is the maximal success probability that is attainable with the usage of P of EMs, and the best success probability attainable with the usage of projective measurements. In general, when you take the best strategy using generalized measurements, you can simulate this strategy via projective measurements with success probability 1 over d. And that would be some strategy that uses projective measurements alone, and therefore you have this kind of a bound for the optimal success probability with the usage of projective measurements. Or when you tweak it, it means that the ratio of the success probability when you use the optimal measurement to the optimal projective measurement is at most d. And I'm interested in the question whether this bound is tight in the limits of large dimensions. Right, so basically it turns out to be tight because you can construct some ensembles of states for which it's saturated. So I don't have that much time, so yeah, basically one ensemble of states is based on so-called uniform ensemble, so it's in some sense symmetric. I don't want to go into details, but for this particular ensemble, you can see that you can asymptotically attain basically this bound. Second interesting example consists of IID high random pure states. D IID high random pure states taken from some d-dimensional space when d is greater than small d, big, yeah. And then effectively one can show that with high probability this kind of ensemble would also attain this bound. So typical ensembles of states that you would have for the problem of unambiguous state discrimination would also satisfy would saturate this bound. Yeah. So the last point I wanted to mention is that my student implemented this on this IBM quantum device. Okay, so to implement generalized measurements, you need ancilla. So when you want to implement 1 qubit measurement, then you need ancilla of the same dimension. So then to implement any unitary, you basically need to implement this kind of circuit. Whereas, for 1 qubit system, our setup is very primitive because you just need to do 1 qubit gates. But the cost is that you need to trash part of the outcome statistics. Okay, and then what we did, we took some figure of merit to compare the results of the experiments with ideal measurements. So we have some measurements that we implement experimentally. We do some tomography on them. And then we compare what we got with the theoretical measurements we wanted to implement. And then for this figure of merit, we basically saw that probably due to yeah, due to noise involved in non-local operations there, the quality of our scheme is, okay, better for various classes of measurements. Okay, but this is just an illustration, I think, yeah. But it maybe shows that there is like a trade-off between the space that you need to implement a measurement, so extra dimensions, and the time needed to do it. Okay, so maybe if you are willing to wait a lot of time, then you can get around without using extra space. Yeah. So to conclude, yeah, generalized measurements. Projective measurements can simulate broad class of measurements if you allow for classical resources on together with them. However, the quality of the simulation is not understood in the limit of large dimensions. If, however, postselection is allowed, let's say more comprehensive and complete results are available. So the optimal success probability can be computed, and it's saturated for this task of unambiguous state discrimination. And in general, in the context of near-term devices, one can expect, as I said before, trade-offs between time and space necessary to implement generalized measurements on realistic devices. Okay, there's a bunch of open problems that maybe I skip for the discussion, if there is any. And thank you for attention. Let me maybe advertise that Gdańsk, the place where I'm based now, got a huge funding recently, and there will be many new openings for PhD postdoc positions in the near time, so stay tuned. Thank you.
Hello. Okay, questions? No? Here.
So Michal, postselection is powerful. Do you expect you could do something similar with some alternative resource which is less powerful?
Alternative. Yeah. So actually, it's in the limit of large dimension. Actually, I don't know if you don't use postselection at all. I don't know what is the gap in a sense. It might be very well that the gap, let's say, between two classes of measurements is in a sense constant. For some, for instance, for the problem of minimal error state discrimination. Okay, so it might be that, let's say, generalized robustness, in a sense of what Barbara was talking about this morning, is basically a constant regardless of the maximal generalized robustness. Aside from this, well, so maybe if one goes to instruments, maybe more can be said there. Yeah.
Thank you. More questions? No? Okay, let's thank you again, Michal.